All right, so welcome to the second video in regards to the physical properties of sound, and this is going to be based on the seventh lecture of the fourth week. We're going to focus on piezoelectricity and what is the piezo and inverse piezoelectric effect. What is electrostriction, magnetostriction, how they relate to one another, how these three are the main players in generation and detection of ultrasound, what is resonance basically, and what is the difference between ultrasound pulse and continuous ultrasound. And basically, we are going to orient ourselves towards what questions can be asked about these topics. But obviously, if you want to go more in depth into these things and become eventually ultrasound technicians, that is all in your power. But right now, we are going to focus on information that we may need to know for basic biophysics course. So let's take a nap at piezoelectricity, and piezoelectricity is basically electricity that arises from pressure, from pressure, and that is the characteristics of certain crystals. Let's just take we have two main players, quartz. We all heard of quartz, and topaz is also quite familiar. So let's just say I have these crystals here. Let's say I'm taking quartz. I'm taking quartz. I'm actually taking this same quartz, and I'm putting it on this side because I'm going to describe two different situations. So this is the same quartz crystal. And what's going on here in this quartz crystal is, let's just say I'm applying compression force to it. If I'm applying force to it, I will get, let's say, a negative charge on this side and a positive charge on this side. I can actually get electricity from it. And if I apply the opposite, let's say tension, which is trying to spread it apart, I will get the opposite charge, as you may well have noticed here. And the question is, how does piezoelectricity work? How do these crystals attain the property of giving me electricity from tension? And let's take a look at this little depiction here that I grabbed off of the Center for Scientific Creations. This is their address, the Center for Scientific Creation. A very cool website. It's got some cool stuff. You can rummage through it in your free time. Well, what happens here is we have a quartz crystal. And this quartz crystal is basically silicon and oxygen atoms. And this is its orientation at its ground, you could say ground state, when there's no energy applied to it. And the important thing to understand here is this crystal, its respective atoms have their charge, where silicon atoms are positively charged and oxygen atoms are negatively charged. And obviously these are the oxygen atoms and these are the silicon atoms. And if you understand their charge, then you already have understood effectively pretty much most of what we need to know. So think of this guy right here. What happens to it when I put tension force? When I put both my hands here, and I pull away. I try to make it wider. What happens? Well, this guy is going to go in, and these guys are going to go away. This is what happens here, as you can very well see. I'm pulling these guys away. So all these guys are going to be pulled away. So how would it look like? It would look like so. It would look like so. And this is not too hard to take in. But what would happen is that on this side here, I would have two silicon atoms that are interacting with this side right here, which means that this side is going to have two positive charges and only one negative charge. Let me switch colors here. So I'm going to have this side is going to come in contact with two positive charges and only one negative charge. So it's going to have a partial positive. Whereas this side is going to come in contact with two negative charges and only one positive charge, which would give it a slightly negative charge, a partial negative. And this is how by pulling this crystal away, I can create a negative charge on one side and a positive charge on the other. So what if I do the opposite? I compress the crystal, the opposite would occur, the crystal will elongate, and I would come in contact, on this side, I would come in contact with one oxygen atom, and that oxygen atom is going to be negatively charged. And on this side, I'm going to come in contact with one silicon atom, which is going to be positively charged. Even if you're thinking, oh, there are two positive charges here, so how come this side is negative? The fact of the matter is that only one atom is in contact with this side here. You just think about this, these two are too far away to influence the charge on this side here. So one side is negative, the other is positive. What you need to understand is when I'm changing, when I'm going from pulling it apart to compressing it, the polarities change. This positive turns into a negative, and this negative turns into a positive. This is really, really cool. But why do I need this for ultrasound? How come we learn about piezoelectricity and ultrasound? Well, the cool thing about piezoelectricity, is that it is, and I'm going to write it down, piezo, and this is very important, piezoelectricity is reversible. First, before we answer this, when we say piezoelectric effect, this is the piezoelectric effect, is just taking tension or compression force, and turning it into electricity. When you're thinking about tension and compression, it's basically mechanical deformation. So if I'm saying this is reversible, what do I mean? That means I can take electricity and cause mechanical deformation. That means that by introducing, let's say, this side with negative and this side with positive, I can cause this guy to change its form and look like this. And it also means that if I inverse, if I change the polarity, and I put, instead of negative, I put a positive charge, I can cause this guy to turn into this. And let's say that I have a negative charge here and a positive charge here, and I'm switching around between these two stages. Basically what would happen is this crystal is going to, you can say, dance between this this mechanical form and this mechanical form. It's going to go back and forth and back and forth. It's going to be wide and then elongated and then wide again. And we said that a mechanical sound wave is just basically having some sort of source that can bring the particles around it into motion by vibrating. So if I have vibration, I have a sound wave. So I'm just going to repeat that. A sound wave is a mechanical interference or a mechanical oscillation of particles that is generated by vibrations. So now I have vibration. I can just introduce electricity and cause vibrations. So how is it used in ultrasound? Just think of me doing this process of back and forth, switching around the electric currents around this crystal super rapidly. Super rapidly. So it's going to go through these transitions. It can go through these transitions a great amount of times in a second and vibrate so quickly that it would emit an ultrasound. Obviously, the quicker I do these transitions from this state to this state, the quicker I do that, the higher the frequency. So if I do it really quickly, I would get a very high frequency ultrasound. And that, taking electricity and causing mechanical deformation, we already said this is going to get us our ultrasound or any sound. This is called inverse piezoelectric effect. And this is now getting useful to us. Because we can take this crystal and we can introduce current to it, and we can cause mechanical deformation and get an ultrasound. Now, this is only going to be introduced a little later in the presentations. but I'm going to cover it now. What we can use piezoelectricity for. Piezoelectricity for. We said we can't use it to generate ultrasound, but we said that we can take mechanical deformation and turn it into electricity. And how am I using it in ultrasound anyways? Let's just say that I have my transducer. The transducer is actually generating and reading ultrasound. This is what they use. So I used the inverse piezoelectric effect here to generate ultrasound. Generate ultrasound. Now the thing is that ultrasound, and we'll learn about that, ultrasound is also being reflected back. And how would I be able to read the ultrasound that is reflected back? Well, think about it. If I only had a way to take mechanical deformation and get information from it, oh, wait a minute, I already have that. It's called the piezoelectric effect. If I take the mechanical deformation I'm getting from these these ultrasounds, because these ultrasounds are going to come in contact with the material and cause them to change their shape, we can basically get a reading of electricity, and that I can interpret as information. So basically, I can use the piezoelectric effect to read ultrasound. Let's just say interpret ultrasound, whereas I use the inverse piezo effect to generate ultrasound. And if you found this to be a little bit too quick of explanations, this is the beauty of rewind. So just make sure that you understand this little bit, because once you do, it should really be intuitive to you, because a lot of ultrasound relies on that. So this is piezoelectricity and the piezoelectric effect. And the next couple of phenomena are really based pretty much on the same principles, so they're really going to be easier to understand. Now we're going to talk about electrostriction and magnetostriction, which I already mentioned just now, that they're going to be considerably easier to understand once we understand piezoelectricity. And piezoelectricity, I'm just going to put it here. Piezoelectricity is basically a relationship between mechanical deformation and electricity. And you can take one, make the other, you can take the other, make that one, and you can switch it back and forth, and this is very useful. Okay? Perfect. So electrostriction is basically what we do is we can take materials, they're called dielectric materials. They're materials that can interact with electricity but do not conduct electricity. You can think of it that way. That is a very simplified way of thinking of dielectric materials. But let's just say dielectric. I'm just going to put it here. This is electrostriction. Put all the arrows in the right way. So what happens here is that I have some sort of I have it in a closed circuit. And what happens is that basically what I do is I introduce current. Let's just say this side is going to be negative, this side is going to be positive, and I'm going to cause deformation, just like we did with the inverse piezoelectric effect, as you can imagine. So what I do is I put positive charges here, negative charges here. This guy is going to maybe shrink a little bit, and as you can imagine, if I shift this and change this around and put positive here and negative here, maybe it's going to elongate a little bit in this direction. So basically what happens is I am creating vibrations. This little dude is going to vibrate, and I can control its vibrations by applying alternating current to it. Alternating current. And this is basically an easy way to say this is me generating vibrations. We already know that generating vibrations essentially means generating sound waves. This is me making an ultrasound. Perfect. Yay me. What we need to understand about electrostriction is that it is non reversible. Meaning that I can't take this crystal, shoot it with ultrasounds. I can't take this crystal, shoot it with ultrasound, and it would give me information in the form of electricity that I can interpret. That would not happen with electrostriction. Let's see what happens with magnetostriction. And also, what's important to understand with electrostriction is the more voltage I apply here, the more the deformation is going to be acute. So if I have a small, let's just say this is my crystal. If I have a small charge applied to it, maybe it's going to shrink like so. If I have a bigger charge applied to it, maybe it's going to be more drastic. But in any case, it's not super important to know. It's just a side note. So let's see what we have as far as magnetostriction. Magnetostriction is something quite similar, but instead of using electricity, we're going to use a magnetic field. So I'm going to have my material here. These materials are ferromagnetic. You don't really need to know these names. I don't imagine. I really don't imagine. But just so you know, these are ferromagnetic materials. Ferromagnetic materials. And these materials just will respond with a magnetic field. We can let's say we have iron or nickel. These are good examples for ferromagnetic materials. This is an I. This is an R. Okay, so how does this work? You can very may well have imagined that I have a magnetic field that I induce to it, and that magnetic field is going to cause this guy to vibrate, and I can use this to make an ultrasound. The nice thing about magnetostriction is that it is reversible. So it is reversible, meaning that instead of applying a magnetic field to it, I'm just going to put let's a little s, a little n, and again, as I alternate the dipoles here, I can actually get it to either contract or elongate or whatever. And now, instead of applying a magnetic field, an alternating magnetic field, and causing it to alternately vibrate and change its form and create an ultrasound, what I can do, being that I already said it is reversible, what I can do is I can shoot this guy, with ultrasound. That ultrasound is going to cause it to vibrate. And when it vibrates, it is going to, form a magnetic field around it. So when it's vibrating in a certain, let's just say it's vibrating up and down. This is just oversimplification, but let's just say I'm shooting this ultrasound at it, and it's vibrating up and down. It's going to give me, let's just say, such an orientation of magnetic field. But then these particles are going to, or rather particles, not particles, this disturbance, this ultrasound is going to cause it to go up and away. So these dipoles are going to switch around. Basically what I mean is that the alternating ultrasound is going to cause an alternating magnetic field. Maybe I made it a little bit more complicated than it should be. So I'm just going to review. What you need to know is that electrostriction is a way to generate ultrasound by applying electricity to certain materials, which are dielectric. These materials will vibrate and give me an ultrasound. I can do that also with magnetostriction, but instead of applying electricity, all I'm applying is a magnetic field, and I can alternate that magnetic field. What I can also do with magnetostriction is I can read ultrasound. This vibrating ferromagnetic material gives me an alternating magnetic field as it reads the ultrasound, and I can interpret this. So magnetostriction reversible, good for reading and generating, as well as piezoelectricity. But electrostriction only goes one way, only generates. Hopefully this is understandable. Let's keep going. And these are two very simple subjects. Well, I wouldn't say simple, but we're not going to go in depth into them. Resonance, and this is just a quote from my own lecture notes. I just found this the easiest way to explain it, so we're just going to read it out. Each material has a specific frequency in which its particles oscillate to the greatest extent. This means that if I have, let's just say, a glass here, let's just say I have a glass, and I can bombard it with ultrasound of frequency X, and it is going to have a certain response. But if I go up and I reach a specific frequency that would interact with the particles of this specific matter in the maximum way, it is going to cause maximum oscillation. I can cause a maximum effect on this object and potentially break it. This is the resonance frequency, the frequency at which these particles have the most displacement to one side or the other. Any glass has a resonance frequency, or this is just an example. Any glass has a resonance frequency in which it is most likely to shatter. That is because the particles in the glass oscillate to the greatest extent when hit with a mechanical wave of that specific resonance frequency. And again, I just want to make sure, maybe I made a mistake and said that the particles are moving to the right and then to the left. They're not really moving, they're just oscillating. This is what they're really doing, they're oscillating. It's not that one particle goes over there and one particle goes over there. Just to make sure that we're on the same page here. So this is resonance and resonance frequency. Each material, a glass A can have a specific resonance frequency. This glass would have another specific resonance frequency. You can have resonance frequency for a table. You can have resonance frequency for a bridge. So really, anything can have a resonance frequency to it. This is a horrible looking bridge. Let's take a look at what is ultrasound pulse and continuous ultrasound. I can't even make it sound very scientific. Continuous ultrasound, just think of it as a continuous wave. Well, obviously, we're not talking about transverse waves, but this is just a way to think about it. It's just the same amplitude. Now, what we need to know is that when we use, let's just say we use piezoelectricity to generate ultrasound, that crystal is going to start vibrating slowly and then pick up the speed to where we set it. Let's just say we set it to 2 megahertz. It's going to start at, let's just say, 1 hertz, and then it's just going to build itself up really, really quickly and reach 2 megahertz and stay there. So essentially, it's going to look, generation of ultrasound is going to look like this. Here, let's say this is where we set it, and this is where it's going to stay. This is this portion here. This portion here is the continuous ultrasound. What is the pulsar ultrasound? And you may already get to where I want to go. Let's just say I want to make 2 megahertz pulse ultrasounds, and this is the 2 megahertz amplitude. Or rather the 2 megahertz frequency with a specific amplitude here. What would happen is when I'm generating a pulse ultrasound, first of all, the inverse piezoelectric effect starts vibrating the material, and slowly I would get bigger amplitudes, and then I would get my target amplitude, and this would be the pulse, and this would stop. And essentially, if you don't know what a pulse is just a mechanical disturbance over a specific amount of time. It's not going to go on and on and on and on. I just want a 1.5 second pulse of 2 megahertz ultrasound. Just an example of what I mean. So this is what a pulse would be. And the difference between a pulse and a continuous ultrasound is that in a continuous, what did I do here? In a continuous ultrasound, this amplitude that we see here is constant. And in a pulse ultrasound, it is slowly building up, this amplitude here. And it's because it takes time for the piezoelectric material to start vibrating to that specific amplitude and the specific frequency we need it to vibrate. This is the difference between continuous ultrasound and pulse ultrasound. Hopefully you found this helpful. These two topics, I find that these two topics are not as important as these topics, electrostriction, magnetostriction, and piezoelectricity. So if you need to, take your time and review this in this video again. Hopefully you found this helpful, and we'll see you on the next video.